Hello, everyone. This is Qin from the Climate Dynamics Prediction Laboratory in Purdue University. In this video, we are going to talk about how to use Cython to speed up our Python code. Well, our application case will be using CMIP6 output to project future trends in mean and extreme values of water bubble temperature. Water bubble temperature, by definition, is the temperature of a parcel of air cooled to saturation by the evaporation of water into it, with the latent heat supplied by the parcel only. Water bubble temperature is one of the heat stress metrics. It incorporates the effects of both humidity and temperature on heat stress. Here is the equation of water bubble temperature, which is a T sub W. We can see that the equation is very complex, is highly nonlinear, and it's impossible to get a simple analytical solution. So we need to use a numerical technique to solve this equation. From the perspective of programming, it means we need to resort to the SciPy optimized function. And also as a demo, we will only calculate water bubble temperature for 2 years, namely the first and last year of this century. And we will compare them to detect the changes in both the annual mean and 95th percentile values of water bubble temperature. We will first define a set of Python function to calculate water bubble temperature, and we will show that it's very slow and it's not acceptable. And then we will show how to use Cython to speed up our code step by step. But before I go to Jupyter Notebook, let's have a recap about what is Cython and why Cython is useful. First, what is Cython? Cython is a programming language, and in fact, nearly all Python code is valid Cython code as well. For example, in the figure on the right side, we define a simple Python function called f, and then we define another Python function to integrate this f from A to B with n steps. These are very simple Python functions, but they are also totally valid Cython code. But in addition, Cython can enable the static type system of C. For example, in the figure on the lower side, this is exactly the same function as on the upper side, but we include some static typing, like the cdef, ss, x, and dx. The static typing over here is actually the key to speed up our code. Well, in addition, Cython is also a compiled language, which means all the Cython source file need to be compiled first in order to run. And this leads to the fact that Cython is also a compiler. It can compile Cython source file into a C code, and the C code will be compiled by a C compiler into a shared object file, which can be directly imported into our Python session. Now, why is Cython useful? Well, as we know, the Python is dynamic, interpreted, and user-friendly. It's easy to learn, but it's slow. While C is static and compiled, it's fast, but it's kind of difficult to learn. And the Cython sits between them and trying to combine the power of both them. Cython did that by compiling Python code, maybe with minor modifications, into C code. In this way, Cython can combine the Python expressiveness with C's performance. Now let's go to the Jupyter Notebook. We import the packages we need. First, we read in some CMIP6 data from the cloud using the intake ESM. For people who have no experience in that, please refer to our first video about climate data access. Here we ask for both the historical and the SSP 585 experiment. We only want one model with 3 outlet frequency. We want 3 variables, the 2-meter air temperature, specific humidity, and the surface pressure, which are required for the calculation of water bubble temperature. We can view the search result as a data frame. The intake ESM can directly load the search result to a dictionary of X-ray dataset. And it also tells us that the keys in the dictionary will be structured as activity ID, institution ID, source ID, experiment ID, table ID, and a grid label. We can see there are 2 X-ray datasets within this dictionary, correspond to both the historical and the SSP 585 experiment. Here we only select 1 year for both experiment, namely the first and the last year of this century. And we will calculate water bubble temperature for both years and then compare them in order to detect the changes in the water bubble temperature. Now, after we access the data, we define our Python function to calculate the weather bomb temperature. We can see there is a lot of function over here. And this is a final function that we use to calculate the weather bomb temperature, and all the things above are supportive functions. And we notice that at the end of this final function, we call this SciPy optimized branch function to solve the equation numerically and return the final result. And since this SciPy optimized branch function is not vectorized, it only accepts a singular input. So that's why we have to use this nested for loop and pass in a singular input within each loop. So as we can expect it, this nested for loop will make our Python function very slow. Now let's try that. Here, we only select the first time step of the historical experiment because we want to say how long it will take for just calculating one time step of weather bomb temperature. Okay, I forgot to define this weather bomb py function. I will need to run this cell. And I run it again. Yeah, it cost me about 4.5 seconds to calculate this weather bomb temperature for just a one-time step. So let's say if I want to calculate 1 year, if it's a 3-hourly resolution, it will cost me more than 3 hours. Now let's imagine you want to calculate for 100 years and 10 GCM. It will take so long and it's not really acceptable. So now we know that its pure Python function is slow, and we will use Cython to speed up that. Cython can compile our Python function into machine code and make it faster. Now, some people may have experience with number. A number decorator ngid can do the similar thing. However, it won't work in this case because number doesn't support the SciPy optimize function, and we'll fall back to the Python mode. And Cython is what we need in this case. In order to show how Cython is useful, let's start from the basics. First, as we have mentioned, Cython is a compiled language. So how to compile or how to build a Cython code? Well, it involves two stages. First, we use a Cython compiler to compile Cython source file, which is a .pyx file, into C code, which is a .c file. Then we use a C compiler to compile the .c file into a shared object file, which is an extension module that we can directly import in our Python session. And there are several ways to implement the two stages, and I will talk about two of them. The first one is using setup tools. It's more flexible and more powerful, and it's also the recommended way to do this. In order to use setup tools, you need to first have a Cython source file, which is a .pyx file. And then after that, you need to write a setup py file. The information in this file will tell the compiler how to compile your code. And after that, we just run this simple command to start the compiling. Now let's use this example to show how to compile Cython source file using setup tools. This is exactly the same function as we have seen in the slides. Since this is a Python version, we call this integrate fpy. Like we have said, in order to use setup tools, you need to first have a Cython source file. We already have it here, this integrate.pyx file. We can see this is exactly the same function, but I changed it from integrate fpy to integrate fcy because this is a Cython version. And except that, I didn't make any changes. That's why I say nearly all Python code is valid Cython code as well. Well, after that, we need to write our setup py file, which is over here. We import the setup from the setup tools and import a Cythonize command from the Cython build. And then we call the setup. The central command here is a Cythonize, which we will call the Cython compiler to compile our .pyx Cython source file. And what we get is an extension module that we can directly import it in our Python session. Now let's run this command to compile our Cython source file. We need to start a terminal. We go to the ret directory. But first, we need to activate the correct environment that our notebook is using. You can see that in this directory, we have this .py as a Cython source file, and also this setup.py file. Now let's copy this command. It's compiling. It's finished. We can see that we have this integrate.c file, which is the C code that compiled by the Cython compiler, and we also have this shared object file, which is generated by the C compiler, and we can directly import that in our Python session. Now let's try that. Let's first run this cell, and then we can do the from integrate import this integrate fcy function. Now let's try the Python version and the Cython version to see if it can give the same results. Yeah, they give exactly the same results, so our Cython version function works. Now let's introduce the second approach to compile Cython code, which is using the Jupyter Notebook Cython extension. This approach is more interactive. The only thing you need to do is you first load this Cython extension, and then you put your Cython source file within a cell, and then you put your Cython source file within a cell, and add a Cython magic command at the beginning of it. If you run this cell, it will automatically compile it for you. And in the back end, it will still go through the two stages, but it's transparent to us. We found that it also generates a report for us. That's because we added this -a, which stands for the annotation. In this report, if we click the plus sign, it will show the C code that it generated for us for each line of Cython code. And also we see a lot of yellow stuff over here. Some are darker and some are lighter. And it says that the yellow lines hint at a Python interaction, which means we need to interact with Python, which is slow. So you can think that the yellow stuff are bad thing and you want to remove it as much as you can. For now, we will live with that. Let's compare the performance of our Python function and the Cython function. Well, we will find that this Cython function will have around 30% performance improvement compared with the Python function. And actually, we didn't do anything. We just add a Cython magic command at the beginning of this cell. So this 30% performance improvement is totally free, and we are happy to take it. And this improvement is because Cython compiled our Python code into machine code. And in this way, we remove the interpreter overhead. But the 30% is not a big improvement. And the real improvement actually comes from static typing. We can type variables like over here. We use the cdef keyword to declare s and dx as double type. We can also type the argument of a function. Now let's see. We found that the yellow stuff becomes less, which is a good thing. And then we see its performance. Well, compared with the initial performance, there is around 5 times speed up. In above, we only type the variables, but in fact, we can also type the function. Well, Python function is flexible and powerful, but it's also expensive. And it's especially expensive when calling from Cython, because it may involve some type conversion between Python and a Cython object. Well, here you find that we can also use the cdef keyword to type a function. Here we declare that this function will return a double type. Now let's compile it. We can see that the yellow stuff is even less, and then we see its performance. Well, compared to initial performance, they are around 200 times speed up. It's a great improvement. In this Cython source file, we find that there are 2 types of function. The first one is the cdef function. It's actually a C function, and it can only be called within this cell. It's also fast, so it's generally used to define fast supportive functions. And this def function can be called both within the cell and out of the cell. But since this is a Python function, so when it's called within the cell, it's generally slow. So we generally use def function to define our final function that we want to use out of this Cython cell. And in addition, there is actually another type of function called a cpdef. And the cpdef function can also be called both within the Cython session and also a Python function. When it's called within the Cython, it's called as a C function, so it's also fast. When it's called out of the Cython cell, it's called as a Python wrapper around this Cython function. So it kinds of combine the power of both cdef and def function. But however, because of this extra functionality, it also involves an extra overhead compared with cdef, so it's not as fast as the cdef function. Well, we have shown that static typing is really the key to the performance improvement. So people may need to type everything at the beginning. Well, actually, this is not necessary because Cython is able to do automatic type inference during assignment. For example, over here, we'll find that I don't type with dx. That's because I have declared the types of a, b, and n over here. So when I do this assignment, Cython will automatically infer the type of dx, so there's no need to type dx. And second, some unnecessary typing may even slow our code because of these unnecessary type checks or conversions. And finally, the most important thing is to make sure typing everything in the performance critical part of the code, such as within the for loop, which means that everything within the for loop needs to be white, such as over here. Well, just out of curiosity, let's compare with the performance of a number ng decorator. We compile it and we run that. And we know that when we run this number compile function for the first time, it will also involve the compiled time. So let's give it a second chance. It's a bit faster, but still, it's not as fast as the Cython version. Except for spinning our code like this, Cython can also make calling external C libraries straightforward. Let's say, for example, some people in your field have developed a model which was written in C, but you only work in Python. Well, in this case, you don't need to rewrite the model in Python. You can use Cython to directly call the C function that defined in the model. And in fact, Cython had already defined many standard C library functions for us, such as the most commonly used standard C math library. When you do math calculations within a Cython source file, you want to use this math function from a standard C math library because it's faster. You don't want to use a NumPy or Python version. And here is a link showing all the math functions that are available in the Cython standard C math library. In the example above, our code just take a scalar input and output another scalar. But in a real world, many of us work with NumPy, and our function generally take a NumPy array as an input and output a NumPy array. Now, in this case, how Cython will help us? Well, let's use a simple example to illustrate this. We define two NumPy array, A and B, and define a very simple Python function. Just add this to NumPy array. And we time it. Well, NumPy is already highly optimized for such simple vectorized computation. Now let's see how Cython will deal with this case. First, we try to naively compile it without any change. And let's time it. There is basically no improvement from the NumPy version. So that is not how Cython works with NumPy arrays. Well, in order to show how Cython can speed up array calculation, let's start from this simple pure Python code, which does the same thing but use a for loop. This is exactly the same function, just add two arrays together, but we use this nested for loop. As we can expect, it should be much slower than the NumPy version of this Cython naively compiled version. And as our first step to speed it up, we just compile it using Cython without any change. And we time it. Again, it only gives us around 30% speed up. And we know that this is because we didn't do any static typing, but how to type an array. And it turned out that we should use this typed memory view. Memory views are C structures that can hold a pointer to the data of a NumPy array and all the necessary buffer metadata to provide efficient and safe access. Well, memory view can also be indexed by C integers and allow fast access to NumPy array data. We can define memory view in this way. We can define a 1D memory view, a 2D memory view, and a 3D memory view of int type. Well, in this cell, we try to add a static typing. We can say we declare the input as a two-dimensional memory view with double type. And here we define a NumPy array called result to hold the result of our calculation. And after that, we define a memory view for it called result view. It's a two-dimensional memory view of double type. And we still use this nested for loop. And within this for loop, we do the calculations and assign the result to this memory view. And finally, we return this NumPy array. Let's compile it and time it. It's much faster than the naively compiled one, but still is slower than NumPy. So NumPy is around 4 microseconds, if I remember correctly. So what else can we do? Well, another thing we can do is using this contiguous memory view. And we can define a contiguous memory view like this. This is a 2D contiguous memory view. By declaring the memory view as contiguous in the memory, we can enable even faster index. So over here, I define all the memory view as C contiguous. And also over here. And you notice that I also add 2 decorator before the function, which can deactivate bound checking and the negative indexing. So let's compile that and also time that. Well, it's a little bit faster, but after all these efforts, we still cannot defeat NumPy. So obviously, we definitely don't want to use Cython for such simple vectorized calculations. So when should we use Cython? Well, before answer this question, let's look at another functionality that Cython offers us, which is using this p-range keyword to enable multi-thread parallelism. In this cell, we further rewrite our code. You can see that here, I import p-range from Cython parallel. And also over here, in the first level loop, I turn the range to p-range. Well, also I add some compiler and link options here, the fopenmp. This will enable the multi-thread parallel computing. Now let's compile this and time this. Well, our NumPy version is around 4 microseconds. And this parallel version is much slower than the NumPy version and even slower than our previous version. So that's because this is really a small problem and it makes no sense to do parallel computing. The extra overhead with parallel computing will make our code even slower. Now let's make our array bigger to show the benefits of parallelism. Let's run it again. Now the parallel function is much faster than the NumPy function, so we can see a clearly benefit of parallelism. So back to the question, when should we use Cython? Well, definitely not for a simple vectorized calculation like a plus b. Well, in fact, Cython is most useful for speeding up operations that cannot be easily vectorized, which means we usually have to resort to for loops. And also, you may only want to use Cython for the bottlenecks of your code and keep the rest of your code still Python. And finally, as we have mentioned, the numbers integer decorator is an alternative in many cases, but sometimes it's not feasible, such as in our case of calculating wet bulb temperature, we need to use SciPy optimize function to solve the equation. And as we have mentioned, the number cannot support the SciPy optimize function. You will fall back to the Python mode. And as a solution, the SciPy team, they developed a Cython API for these optimized functions, and they encourage us to use Cython function. And within the Cython code, we would be able to write a fast for loop at C speed and call this Cython optimized function within each loop. Well, after showing how Cython can speed our Python code in several ways, let's try to transfer our Python version function for calculating white bulb temperature to a Cython version. And here it is. You can see we add a lot of static typing. And as we have mentioned, they are really the key point to the performance improvement. We have a bunch of cdev function, which is a fast sportive function. And our final function is a dev function because we need to access that out of this Cython session. We also add this decorator over here. And we define a bunch of memory view. This is contiguous memory view. Here we use prange to do multi-thread parallelism. And we also add some compiler and link options. This FOpenMP will turn on multi-thread parallel computing. And this OFast will further optimize our code. Now let's compile that. Since our Cython function require 3D output of double type, so we need to first transfer our one-time step 2D slices into a 3D array and also change it from float to double type. Let's run that. Well, you can see it's nearly 200 times speed up. Now, if we want to calculate for 1 year, it will only cost us 1 minute instead of several hours. So it's really a huge improvement. That's how Cython speed our Python function for calculating wet bulb temperature. And that's all I have for this video. Thanks for watching and see you next time.